Okay, Unit 4, Equilibrium, IB Topic 7. Okay, this is a diagram we'll look at in a few minutes. It's concentration versus time. You can see as time goes by, the concentrations of both the reactants and products, so we'll see level off and remain constant. Chemical equilibrium. We have two definitions that we use for chemical equilibrium. The first is the state at which the forward and reverse reactions occur at equal rates. So reactants to products can go back from products to reactants. Going from left to right, we refer to that as going in the forward direction. Going from right to left is referred to as going in the reverse direction. Another definition is the concentration of all reactants and products remain constant. Nice little analogy of this. Imagine ants going back and forth, each one taking a grain of sand to the other. And so even though you have this movement of sand particles going back and forth, the amounts on the reactant side remain constant. The amount on the product side remain constant. Okay, now the double arrows here, this is just a little FYI. You can use any double arrows that you want. You know, a full double arrows, half double arrows. This is typically the way that I use it on the whiteboard, draw it on the whiteboard. Or you could just a single arrow with two heads on it. That's fine. Any one of these would be fine. Example, saturated solutions. So imagine that you have sodium chloride and you simply dissolve it in water. Well, of course, the solid sodium chloride, the ions will become soluble and dissolve in the water. But let's look at this in a little bit more detail. Watch this video.
Sodium chloride crystals are held together by attractive forces between the positively charged sodium and negatively charged chloride ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them. Likewise, the oxygen ends of water molecules are attracted to and surround the positively charged sodium ions. The hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions. Gradually, the entire crystal dissociates into solution.
Okay, but now imagine that you just keep putting sodium chloride into the water. Just keep putting it in, keep putting it in. Eventually, this solution is going to become what we call saturated, meaning that no more salt is going to be able to dissolve. And if you put any more in, it'll just sink to the bottom. When the solution becomes saturated, the reaction will begin to reverse itself. So now we're using two-way arrows, double arrows. So the solid sodium chloride is dissolving at the same rate as the ions are reforming the solid. Okay, you have arrows pointing in both directions now. So the solution is saturated. We have solid sodium chloride forming at the same rate as it's dissolving. Both forward and reverse reactions occur simultaneously and continuously. This is called dynamic equilibrium. The term dynamic means constant change. Okay, now we've already looked at these two definitions. Forward rate is equal to reverse rate, and concentrations remain constant. Here's a nice little analogy for this, something nice visual.
To understand dynamic equilibrium, consider two rooms connected by a revolving door. 30 people have been crowded into only one room. So to get a little breathing room, some people move into the next room. Eventually, equilibrium is reached. In this example, it's when there are 20 people in one room and 10 people in the other. At this point, the number of people in each room doesn't change, even though each room has a different concentration of people. Notice, too, that equilibrium is dynamic. People are still moving back and forth, but they are moving between rooms at the same time and rate. Chemical reactions in equilibrium behave in a similar way.
Okay, so at equilibrium, you have 20 people on the left and 10 people at the right. But as she said, you can see people are moving back and forth at an equal rate. So even though you have that dynamic movement of people from one room to another, the concentration, the number of people per room, remains constant. Now notice they're not equal to each other, 20 on the left, 10 on the right, but they remain constant. Okay, let's look at this reaction. This is the synthesis of ammonia. This is called the Haber process. It's nitrogen plus hydrogen gives us ammonia. We're going to be plotting the concentrations of the reactants and product as time goes by. Okay, now let's say at the very beginning we have this amount of hydrogen, this amount of nitrogen, and no ammonia. And as time goes by, of course, the reactants are being used up, so they go down, and the product is forming, so it goes up. You can see that the hydrogen is being consumed at a much faster rate than the nitrogen, and that's simply because of the coefficients of the balanced equation. 3 moles of hydrogen react for every 1 mole of nitrogen, so it's being consumed at 3 times the rate as nitrogen. Now eventually, the concentrations of the reactants and products will level off, and this is what we call the equilibrium point. The equilibrium point is when the concentrations remain constant and the forward rate is equal to the reverse rate. Concentrations remain constant. The law of equilibrium. Now what we're going to do is we're going to be using this as a generic equation, where the lowercase letters is the coefficient of your balanced equation, and the uppercase are the substances, whatever they might be. Now, for equilibrium, you're also often going to be given information that you don't need regarding temperature. So in this case, if at a given temperature. Now, the reason for that is because the equilibrium constant that we'll introduce here in a second will be dependent upon what the temperature is. So for all equilibrium problems, they will often say, or for many, they will often say at a given temperature or at 825 degrees Celsius, just to be clear that the value of the equilibrium constant will change if the temperature changes. So we have to specify at a given temperature. Okay, so at a given temperature, then, and here it is, this is the equilibrium constant. We use a capital K with a subscript C. Now, sometimes you'll see capital K with an EQ as your subscript, and I kind of like that. I prefer that, but IB uses a C, so we use a C. So you can call this Kc or simply the equilibrium constant, which is what I'll call it. Okay. So if this is our chemical reaction, then we can determine the value of the equilibrium constant by plugging in the concentrations and the coefficients into this algebraic relationship. This is called the equilibrium expression. And what it is simply the concentration of the products in the numerator raised to the power of their coefficient. So concentration of C raised to the power of C, whatever the coefficient would be for the balanced equation, times the concentration of D raised to the power of D. And again, those are the products in the numerator, and exactly the same idea for the reactants, which are in the denominator. We'll do some practice problems on this in a bit. The value of the equilibrium constant will be constant for any given temperature. So if we have actual numbers here, we know the concentrations and the coefficients, and plug in all those numbers here, we'll get a value, a literal number for the equilibrium constant. And that number will remain constant as long as we don't change the temperature. If we change the temperature, then the number would change. So that's why we always have to say at a specific temperature. Okay, so this is just to refer to we're going to look at the value of K, of the equilibrium constant. There's three possibilities. It could be greater than 1, less than 1, or equal to 1. Let's first look at if it's greater than 1. Well, if it's greater than 1, what does that mean? Well, looking at the expression, the products are in the numerator. So in order for K, the equilibrium constant, to be greater than 1, then the numerator must be larger than the denominator. So it must mean that when it goes to equilibrium, we have more products than we have reactants, because the numerator is a larger number. So what we say is that the reaction is product favored, meaning that after it goes to equilibrium, the reaction finally gets to equilibrium, we'll have more products than reactants. And if the equilibrium constant is less than 1, then it's just the opposite. It must mean that we have more reactants than products, because the denominator must be the larger number. So we say the reaction is reactant favored. And if it's equal to 1, well, then it's neither reactant nor product favored. Now there's another way of looking at this. What if the value of K, of the equilibrium constant, is really large, not just greater than 1, but really big, or really small? Well, that also gives us some information. This is called the magnitude of the equilibrium constant. If the equilibrium constant is much greater than 1, now there is no definition on exactly what number, and this is the way that we refer to it as. If it's much greater than 1, well, what does that mean? That means that the products is a very, very large number, and the reactants are a very, very small number. So for all intents and purposes, we can say that the reaction has gone to completion. That when the reaction took place and it finally reaches equilibrium, we have almost entirely just products, virtually no reactants. So the reactants are very, very small. So we can say the value of the reactants goes to 0. Well, if it goes to 0, well, then Kcu would go to infinity. It's not going to, but it would get very, very large. And just the opposite, if the equilibrium constant is very, very small, then we can say that the reaction essentially didn't take place. Because if the equilibrium constant is really small, well, that must mean that the amounts of the reactants is very large and the amount of the products is very small, meaning that we've made hardly any products at all. So the reaction just essentially didn't take place. Now, the actual value of the equilibrium constant is usually somewhere between 100 and 100th. It can certainly be greater than 100. It can be less than 100th. Kind of depends upon the particular reaction, but that's kind of the general range. And in that range, both reactants and products are present in easily noticeable amounts. Imagine if this was a acid-base reaction. Well, let's say that we had an acid as a reactant. Well, that's going to cause the pH to be very low. As the reaction progresses, the pH is going to go down as the acid is used up. So if the concentration, or if the value of the equilibrium constant was between this, well, then we can measure the pH relatively easily. All right, now let's look at phase and the equilibrium constant. Now by phase we mean a solid, liquid, gas, or aqueous. The equilibrium constant is independent of solids and liquids, as their concentrations do not change. Let's use water as an example of this. If I had 1,000 milliliters of water, that's 1,000 grams of water, I would have 55.6 moles, which is an easy calculation. Remember, the molar mass of water is 18.02. 1,000 milliliters of water is 1,000 grams of water. So 1,000 grams divided by 18.02 is 55.6. So in a liter of water, we have 55.6 moles. So we could say that it is 55.6 molar. Well, what if I had half the amount, 500 milliliters? Well, I would have half the number of moles, but I still would have the same concentration. And so that would be true for a solid and for a liquid. The amount that we have, it does not change. So solids and liquids are not included in the equilibrium expression. So when we come up with our equilibrium expression and we have a solid or a liquid, we simply omit it, as you'll see here. Homogeneous equilibria. One phase is present for all reactants and products. Homogeneous means the same. So for example, in this reaction, nitrogen and chlorine to give us nitrogen trichloride, all of them are gases. And so when we write our equilibrium expression, so we have our product is nitrogen trichloride, so that goes in the numerator, raised to the power of its coefficient. And in the denominator, we have nitrogen. The coefficient is just 1. For the chlorine, the coefficient is 3, so it's a concentration of chlorine raised to the third power. So this is our equilibrium expression for this reaction. And this is an example of homogeneous equilibria. Okay, let's look at heterogeneous. In heterogeneous equilibria, we have 2 or more phases present. So example, carbon, which is a solid, reacting with liquid water to give us gaseous hydrogen and carbon monoxide. I laugh because what else is hydrogen going to be? So when we write our equilibrium expression, we need to keep in mind that we do not include solids, we do not include liquids. We simply omit them. They are not included in our equilibrium expression. This is our equilibrium expression. Kc is equal to this. Now I've included it here just for instructional purposes, but you would not need to include it at all, or you shouldn't include it at all. We simply pretend like anything that's a solid or a liquid, and could be on either side. If it's a solid or a liquid, simply ignore it, omit it from the equilibrium expression. Okay, now let's take a time out here for a minute to make sure you can use your calculator correctly when you raise numbers to a power. To raise numbers to a specific power, the simple way to do it is to use the y to the x key. Now, of course, some of you have other calculators, and you have a calculator with that little caret on it. You can use that too. But on the calculators that we use in our class, and maybe you have checked one out, it's this key that's right below the off key, y to the x. So let's do an example here. Say we have 4 to the third power plus 2 to the fourth power. Well, to type that in, I would go 4, type in 4, and then hit the y to the x key. And when you do that, nothing's going to happen. But then type in 3, and then plus 2, and then hit y to the x key, 4 equals. Now, if you did that correctly, you should be getting 80. So when you try that yourself, pause the video, make sure that you can get that. Okay, let's try another. What if it was 4 to the third power times 2 to the fourth power? Try that. Think you're so smart. Okay, so hopefully you're going 4, and then hit y to the x key, 3, times 2, and hit y to the x key, 4, equals. And you should get 1024. Okay, let's practice using an actual equilibrium expression. So we have this. So see if you can do this. Now remember, anything in the denominator we divide by. So it would be this divided by this divided by this. So when you try that, see if you can get it. All right. So you would be 0.5 to the fourth power, using the y to the x key, divided by 0.1 to the third power, divided by 0.2, and you should be getting 312, 3 sig figs. Okay, you might want to practice that a little bit before you continue, because we're going to be doing some actual calculations here in a minute. Okay, practice. Calculate the equilibrium constant for the following equilibrium system. So this is our equilibrium system. And you're given these as our equilibrium concentrations. So at equilibrium, these are the concentrations that we have. Remember, in the brackets are used to mean molar, so moles per liter. Okay, now I'm going to throw in here the temperature as 285, but again, It's often given, never needed. It's just when we are asked to calculate the equilibrium constant, it will change depending upon the temperature. So temperature is often included just to kind of set the stage that it's at this temperature. Okay, so now to do this, first we want to write our equilibrium expression. So that's be the first thing you'd want to do. So nitrogen trichloride raised to the second power divided by nitrogen and chlorine raised to the third power. So now we can plug in the numbers. Now don't use brackets when you do the actual calculation. The brackets is a shorthand meaning molarity. After that, it's just a regular calculation. So you don't even really need the parentheses. It's by good form to use parentheses when you're raising something to a certain power. But anyway, so this is the concentrations raised to the correct powers. So plug that in, and you should be getting 1.45. Now, if you're not getting that number, practice it a little bit. So again, be 0.1 raised to the second power divided by 0.5 divided by 0.240 to the third power equals. Let's try another one. Oh, sorry. Note, units are not required. We are only interested in the magnitude of the equilibrium constant. So remember, the magnitude will tell us to what if it's reactant favored or product favored. So it's greater than 1 here, so it's product favored. It's not much greater than 1, so we will still have a certain amount of reactants remaining that will be easily detectable. Now, in higher level IB chemistry, we will be paying attention to the units. But for our purposes, for standard level, we're only interested in the magnitude of the equilibrium constant. Let's try this. Calculate the equilibrium constant for this reaction. Now this is a heterogeneous equilibrium. We have solid and we have solid here and solid here. So we only need the equilibrium concentrations for that which is not a solid or a liquid. And so in this case, it would be the hydrogen gas and the gaseous water. So that's why we don't have any data for the solids, because we don't need it. So the equilibrium constant will be the concentration of the products raised to the power of its coefficient. In this case, it's just water raised to the power of 4. And for the reactants, it's just the hydrogen raised to the power of 4. So plugging in the equilibrium concentrations that were given. Again, you might want to try this yourself. 0.583 to the 4th power divided by 1.52 to the 4th power, and you should get 0.0216. Okay, that is it. That is the end of notes.